Can you hear me?
I can hear you all right.
Okay. So, most welcome to our day's CM Talk series, where we host speakers from different backgrounds to come and take us through on what they are doing. So today we are going to be hosting our Vice President, Yao Gahounzo, who is working with Professor Kopera. So he's going to take us through his internship work he did over the summer 2022. That's very cool. And the topic of this talk is unimproved big-grid formulation for the dynamics of MPAS Seaice. So Yao Gahounzo is a third PhD student here in the computing program, and is working on ocean modeling with Professor Kopera. He has a master's from MPAS in mathematical sciences and a bachelor's in mathematics from University of Lome, Togo, and is a Togolese by birth. So, Yao, can you please take over?
Oh, sure. Thank you so much, Brian. Can you hear me? All right. My today's presentation will be on an improved big-grid formulation for the dynamic of MPAS Seaice. It's a project I did over the summer during my internship at the Los Alamos National Laboratory. And these projects have been supervised by my two mentors at the lab, Giacomo and Mark Peterson, and they are the scientists in computational physics and the method group at the Los Alamos lab. My presentation will be on MPAS Seaice, the dynamic of MPAS Seaice, how to solve the dynamics that describe the model MPAS Seaice model. And the MPAS Seaice is the component in the ETSM model. ETSM stands for Energy Exascale F System Model, which is a climate model developed by Department of Energy. And as we know, climate model have different components. So ETRMs also have different components. We have like a ocean model, we have atmospheric model, and also we have the sea ice model, and then land ice model. So that's what I'm going to talk about, and the MPAS Seaice model. About MPAS Seaice can be used as a coupled model with ETSM. At the same time, can be also used as a standalone model, just so for the simulation of the sea ice. So the overview of this presentation, or the outline of this presentation, I'll briefly talk about what is important of modeling the sea ice, and also talk about the dynamic of the sea ice, since sea ice, as we know, is a moving body. So there are different forces that act on it. So I'm gonna describe those first, and try to talk about the numerics used to solve that dynamic in the MPAS model, and also probably present some of the numerical results, and highlight a little bit the climate simulation using ETSM as a coupled model. So sea ice is a major component in the global climate system because due to its high reflectivity, it helps reflect a huge proportion of radiation coming from the sun back to the atmosphere. And also it helps increasing the planetary albedo. So therefore, it is crucial to know the evolution and how to know the role it plays in the global climate system. And if you consider an open sea without ice, the research show that about 94% of the radiation coming from the sun is absorbed by the ocean, making the ocean dark. And as the ocean become dark, become also warm and melt the ground ice shell, and causing like problem to living quantities in the ocean. So if you consider the icy body as a moving body, there's what we call internal stress of the sea ice, and that internal stress acts as a regulates the deformation of the sea ice, and also act as a resistance to the motion of the sea ice. Therefore, it is crucial to know how to represent that, or to solve that accurately, that internal stress, in order to represent or predict accurately in the ocean model or ice model the evolution of the sea ice. So the dynamic of MPAS Seaice is basically described by the momentum equation represented by the equation on the slide. The left term represents the initial term for the velocity, and we have the divergence of the stress, the first term. The second and the third represent the external stress due to the atmosphere and ocean. And we have the first due to the Coriolis force and the first due also due to the sea surface heights, because as we know that the surface of the ocean is not always flat. So that's also due to have some personal force on the sea ice. But in this presentation or on my work, I'm mainly focused on this, how to solve numerically the first term on the right-hand side, which is the divergence of the stress. Because as we know, it's a challenge to solve numerically in the numerical or in the ocean model or the sea ice model. So on the figure on the right, we can see the different forces that act on the sea ice body. As on the orange, we can see the internal sea ice stress that regulate the movement or the deformation of the sea ice. We also have the stress due to the ocean, the current, the ocean current also acts on the sea ice. We have the force due to the wind. We also have this force due to the Coriolis force and also the sea surface forces. So from now on, the rest of this presentation will be how to solve numerically the first step, which is the divergence of the stress. But before that, we also need to derive if we consider a domain in which we want to solve this problem, we consider a domain and then we discretize that domain into small chunks or small cells. So in MPAS model, we adopt a approach called the big grid approach, where we consider the velocity components in the dynamic equation, in the momentum equation, and we place those quantities of the velocity inside the cell at the cell center. So that's what we call the big grid approach. And the other quantities like mass or the sea ice concentration, they are places on the vertices of the cell. So that's what, and then this is the standard or the regular and the normal way of applying the big grid method. But in MPAS adopt a different grid technique, how they call the hexagonal grid, like they are polygons with n of size n with n greater or equal to 3. And if you consider this is one of the cells we mainly use in the MPAS model, and we have the cell center where we can place the velocity, but no, that's not how we do it. So I'm gonna talk about how we solve those velocities and where exactly we place the velocity in the big grid here and how we solve it. And the black arrow are just like the coordinate system on each vertices. So each vertex have their own coordinate system. So that's how we basically solve this problem using the big grid approach. But before going, we also need to have a broader view of what is that divergence of stress. How do we compute it? So the total work done by the internal stress, like the internal stress of the sea ice is equal to the displacement of mechanical energy over a given domain. For example, if you have a given domain, omega, the total work done by the divergence of stress is equal to the displacement of mechanical energy. And that is described by the first integral equations. And then that equation, we have the sigma, and the sigma represents the stress, the internal stress. Then the epsilon represents the strain rate tensor. So those are two different components. And we also need to solve those components differently in order to solve the whole system. So in order to solve that integral, we apply the technique we call the variational approach, where we expand that integral using the basis functions. And so how do we expand? Because we expand, first of all, the different component of the velocity. For instance, we take like a different component, we start u, v, sigma. We expand those quantities using the basis function. And that expansion leads us to those integrals we can see on the slides. And mainly, those integrals are the differentiation integral, for those who are familiar with that term. And also the first two ones represent the differentiation matrix, and also the last one represents the mass matrix. And in this context, we can use two different basis functions. we can either use the piecewise linear basis function, or we can also use what we call the Weierstrass basis function. And the V, the domain on which we are solving this problem, is we call the V, and is the union of the grid cell on a given vertex. If you consider a domain and we discretize that domain into hexagonal, using hexagonal cells, for a given vertex, we have 3 cells that are connected to that vertex. So the union of those 3 cells are the domain on which we are solving those integrals. And remember, I just told you that in the big grid approach, we normally solve the velocity at the cell center. But in the MPAS, we adopt two mesh approach. The first one is the regular hexagonal mesh, but the second one is the triangular, that you can see the transparent triangle in that union of the cells. And we place the velocity component at the vertex, and that vertex represents the center of the new triangular mesh. And that's on that mesh we solve now these problems. So to solve that, MPAS initially adopt a technique where, in order, if you are in the spherical domain, and we call that technique as a standard approach because we are proposing a new one. So we call this, the existing one, as a standard approach. And the new one, we are going to call it differently, the projected big grid. And in this approach, each cell is projected, if you're on a spherical domain, for instance, each cell is projected onto a tangent plane at the cell center. So even though we are solving the velocity at the vertex that are connect those 3 cells, but we project each cells individually onto a tangent plane and then solve the velocity component and the contribution of divergence of stress from the combination of those 3 cells. So that's how they solve the problem in MPAS Seaice. But over the summer, we propose a different alternative. Since we are solving the velocity component at the vertex that connects all those 3 cells, we propose a different techniques, where instead of projecting each cell individually on each own's individual tangent plane, we projected the 3 cells that connect to that vertex onto a common tangent plane, and then we solve the divergence of the stress and the velocity component at that given on that given tangent plane. And this is only valid when you are on spherical domain. So if you're on a plane or a rectangular plane, this technique is not valid. So it's only valid when you are on a spherical domain. The 3 cells, instead of projecting them individually onto their own tangent plane, we project the common, all those 3 cells together onto a given tangent plane at that vertex. And then the contribution of the divergence of stress from those 3 cells are then computed on the same tangent plane. So that's the new technique we use over the summer in order to, with aim to improve the numerics used in the MPAS Seaice model. So after doing this, we came up with some analysis tests. First of all, by running some test case for the same rim tensor, string rate tensor, by first of all comparing the error between the standard, the existing approach, and what we propose over the summer. And we can see that there's not much difference between the 2 approaches here. And the main reason here is that the way we compute the strength rate tensor in the MPAS is the same way as whether we use the standard approach or we use the projected approach, because we still use the information from each individual cell. So we are not using the common cell to compute the strength rate tensor, but we use each individual cell information to compute the strength rate tensor. So that's why we do not see much difference in these results. But by continuing, we run this using a very uniform grid cell where there's no distortion or anything like that. We use the perfect uniform grid cell to run this test. So we have another test for divergence of stress in order to see what are the differences, how the impact of this new approach compared to the existing one. And what we did, we also ran this using the uniform mesh. And we can see that there's some differences, or there's a difference between the standard approach and the projected approach. And in the numeric, we all know that as we increase the resolution, we expect the error to decrease. That's one primary goal in numeric. As we increase the resolution, you expect your error in the solution to decrease. But as we can see, the standard approach that the dashed lines, the error does not increase, and that is more visible when we consider the L infinity norm. The error is not that decreasing compared to the new proposed approach, where we see that the error is indeed decreasing. So that's one approach. And this is when we run this is the U component of the event of stress, and we run this using a linear polynomial basis function, and we also run the same using the different basis function as like Wasprash, and we see that the result is similar. So the next one is that, okay, since we run this problem using a uniform mesh, even though we see difference between the error or the two numerics, we want to see what happens when we were in a case where we are not using a uniform mesh, but we are rather using a distorted mesh. So in that context, we use the distorted mesh on the left. That's the mesh we used, and then in the middle we have the result from the standard approach, and then the proposed result is on the right. And in the pink color represent the error between the numerics and the analytical solution we are considering. And the more those pink are visible, means that we have more error in the numerics. So obviously, we see that in the standard approach, we observe more error compared to the proposed approach, where the error are not that reduces. And this also is run using the piecewise linear function. And at the same time, we consider only one component of the derivative of strength, which is the U component, because the other component gives us a similar result. So, but to have like a better understanding of this technique, we run a different analysis by trying to change the resolution to see if we increase the resolution, how does this result look like? Is there any improvement, or is get worse? So in the standard approach, we can observe that the error is not that decreasing as we increase the resolution. But if you consider the projected approach, the error is decreasing, especially if you consider the L infinity norm here. We can see that the error is almost constant when we increase the resolution, but which is not a very good sign, as in the numeric we expect the error to decrease. But rather, if you consider the projected approach, you observe that for the last two resolution, you see that as we increase the resolution, the error is also the error decreases. And this is a very good improvement in the numerics on what we have been using so far in the model. But our goal is, yes, we solve the numerics, which is fine. We have an improvement in the model, which is fine. But how does this affect, if in the context of the global climate simulation, if you want to run the whole entire Seaice model, how does this affect, rather than just solving the divergence of stress? So we run the test simulation using the E3SM, which is a climate system F-class system model. And due to the time constraint over the summer, we couldn't run this for longer. And we just ran this simulation only for 1 year using a 10 to 30 kilometer resolution grid. And in this, we do not see much difference between the two numerics here, whether we use the standard or we use the projected approach. We do not see that much difference in the both numerics. And this result is the error, or is the difference between the output of our model and the observation data. So that's what we have on the slides. And this also is telling us that there may be some other thing we are not considering in the model. For instance, if you want to see a change in the climate, first of all, we need to run this model at least for a decade, like at least 10 years, in order to see a change in the climate. We cannot run a model for 1 year and expect to see a change in the climate, because the climate takes long in order to things to get to affect the climate. And on the other hand, we also have to think differently, because does only numeric count for climate models? Obviously no, because we have, if we consider the sea ice model, we have the impact of the ocean current on the sea ice. We have the wind stress on the sea ice. Also, we have the sea surface temperature. All those parameters affect the climate model. So it's not just the numerics that affect the model, but the other parameters also affect the model here. So, so far, that's what we have done. And due to the time constraint, we did not run for this for longer. And in summary, we conclude that the proposed method we propose here reduce the error in the numerics, improve the convergence on the idealized case, and also the method proposed here improve the climate a little bit, not that difference, but if you take a closer look at those previous results, you'll see that there are some differences. And we cannot state that, oh, there's an improvement or not, but we observe that there's a change in the climate or the result we observed. And for the continuation of this work, we propose that in order to see a very good change in this numerics or the impact of this numeric, we need to run this for much longer, first of all, and second, run this using more idealized test cases, and even using like more high resolution grids in order to resolve the linear kinematic features, because those are the important features we look into sea ice, the deformation of the sea ice, the rate, the friction, and all those stuff. We also look into those in the MPAS. So if you can see these differences from those features, we know that, oh, there's an improvement in the numerical we are proposing here. So that's all I have for today. And here are some of my selected references I used over the summer. And then thank you for your attention.
Thanks very much for, thank you, Yao, for the presentation. Any questions?
Yeah, go ahead.
Yeah, Yao,
Yes.
I think I have a question.
Yeah, go ahead.
Maybe just a general question. How long did it take for you? Because you mentioned that you didn't have much time to run the F system model. How long does it take, as in the computational time?
Well, the computational time for this model to run for 1 year. 1 year we are running for at least 2 days.
Okay, thank you.
Yeah, but the one reason why I'm saying that there's not much, because if you submit a job, you have to wait too long in the queue. For instance, to get that job, I wait in the queue for at least a week in order to get that result. So it's not about the model is not running faster, but it's challenging to get in the queue to run your job, because over the summer, there are many students running their jobs.
Okay.
Can you say which machines you've been running this on?
Well, I use Corey, and Corey is at the Berkeley National Laboratory. So I created an account and then I ran the code from it.
That's cool. So you got exposure to how it really looks like in the wild.
Oh,
you
yes.
can have a fast machine, but you don't have access to it immediately. That's cool.
Yeah.
I don't have a question, but I have a comment. It is, I mean, what you said is really interesting, that you can create a fantastic improved numerical method, yet apply to a realistic model of something as complicated as climate. It might not matter, or as you say, you might not see it immediately because the effect is small compared to other signals that you're getting. So that's also a good consideration for us mathematicians, that we cannot stop at idealized test cases, and even if the method is improved, it still might not change anything, right? Possibly. That's pretty cool. I like that you've seen that in action, right? It wasn't you observed this phenomenon.
Yeah.
But you're right. I wonder what would happen if you run this climate for like 100 years, right? If you actually got a difference or no, with exactly the same parameters, and forcing on both those simulations. That would be cool to see.
Yeah, that would be very nice to see too.
So any plans on continuing with this work, or you just left it as is last summer and there's no going back?
Well, if I go back, I'll probably continue, but I don't know yet if I'll go back.
Cool.
Yeah.
All right, good work. A nice presentation. Thank you.
Thank you so much.
Other questions?
Well, I have one more if nobody else is asking questions. So did you get to implement this new method in the DSM or in MPAS Ocean, or were you just testing it?
No, I implemented this in the
Nice. That's so. Was it difficult to work with MPAS or was it easy?
Yes, the first week was challenging because the code was code is so big and I have to understand everything in order to implement this new numeric thing into the model. But with some sleepless nights was funny.
Okay. That's cool. No, I mean,
it was
that's
good. It
impressive.
was good. The code was challenging, but I have opportunity to work on a very big code and figure out everything. It's good.
Well, that's impressive because it's not, it's not like everyday skill that you just take a gigantic new code and you introduce new numerics to it. That's something else. That's very well done.
Yeah.
And you showed it worked. Like the idealized case shows clearly that you didn't mess it up, right?
Yeah.
Well done.
So I even ran some other test cases, but I did not include them in this presentation.
Sure.
So is there a copy of this work available on GitHub or anywhere?
No, I did a poster presentation at the end of the summer. So if you want to learn, you can just go to my ResearchGate to find out my poster over there. It's the summary of everything I presented here.
Yeah, you should say it's top secret, and now you have to kill us all because we've heard too much.
Yeah, because I was finding a report, but I cannot share those reports because I did not have like an approved of sharing those reports yet. But the poster, for instance, this LUR code, it does allow me to show you this because without that LUR code, I cannot show this report. Yeah. So, but my poster is on ResearchGate. You can take a look if you want.
So can we put the talk on our platforms, or it is
feel free to.
High security? Yeah. Okay.
No, sure, that's fine. You can post it.
Okay. Right. No other questions? Yeah, so I have a question to Prof. Prof, we wanted to be able to use the email for the chapter to be able to set up calendar meetings, invites and stuff. So right now we are just delegates, so we're unable to do that. Hello? I think it's good. Okay, guys, thanks for coming.